So now we have the presentation of Ofer from UCL, who's going to talk more about some new results from the DESI experiments and the dark matter map. So this is very topical, and I hope we'll find the links to Tuomo's blog. Thank you.
Yes, so thanks very much for the kind invitation to give this talk to this forum. It's kind of probably if I gave this talk a year and a half ago, it would have been pretty boring. But now things have happened past year and a half, and it's actually some suggestions that dark energy is not just a constant, so not just a cosmological constant, but it may evolve with time. So it fits in well with the term dynamic universe, although it's somewhat different context, but I'd be interested to hear your opinions on it. So this talk would be, this is a highly theoretical audience, this will be quite observational, trying to connect the two. And really, I think we're fortunate to be in a field that you can go all the way from the philosophy to the engineering. It's only the same field, which I find quite interesting over the years. So what you see here is one survey, which is called Dark Energy Survey, DES in short. And this page is a reconstruction of the dark matter using gravitational lensing. This is just for orientation. That's the Milky Way, targets formed giant clouds. I'll come back to that map later. And this is a map from a different survey, DESI, Dark Energy Spectroscopic Instrument. Each dot here is a galaxy. This is line of sight. And this is the survey that combined with some other data leads to this possible notion of evolving dark energy, okay? And I would like to emphasize the question mark at the end of the title, okay? We don't know it yet, okay? It's under investigation. So this is a brief outline. I want to go through a bit of history, especially the philosophers in the room, put in context. To talk a bit about dark energy, all the way back to Newton, by the way. It's little known. Is it just lambda, the equation of z minus 1? Should it be on the left-hand side or the right-hand side of the equation? There's this very disturbing problem that actually the prediction from particle physics is that dark energy should be 10 to the power 120, larger than what we measure. This problem is so big that people almost don't discuss it at conferences. And then is it dynamical, when to stop, and a little bit about AI and cosmology. So I think a variation of this plot was already shown. I think it's reasonably well established, especially from the cosmic particle background, that the universe is 13.8 years old, and that it's for 25 years now, I would argue even longer than that, the same paradigm that the universe is accelerating. Okay, there's a paradigm shift due to the work on supernovae as standard candles, although there was some evidence for that even earlier. I think everyone knows that at present, very important to emphasize, these are round numbers just to make it a bit nicer. 25% ordinary matter, 25% core dark matter, 7% dark energy. And this is I think it's fair to say that the relativity still seems to work pretty well. I mean, people test it, but it seems to do a pretty good job. Same as with quantum mechanics. About 100 years and over are doing really well. All right, so a little bit of history here. So a number of things. One is that this equation, Einstein's field equation, is still the form that we use. It's worth emphasizing that Einstein actually put the lambda term, cosmological constant, on the left-hand side. Okay, meaning it's part of the curvature. Later, I believe it's attributed to Zeldovich. People start putting lambda on the right-hand side. And refer to it as dark energy and refer to this fluctuation of the quantum fluctuations. So no, so I think this lambda, we still don't know where it should be, left hand side, right hand side. Even if you measure it very accurately, you still don't know that. So either there is everywhere in this room some dark energy, you know, in whatever units per centimeter cube, or it's just a constant, like capital G question.
Sorry, it's a scalar quantity, right?
Yeah.
And it's commute. So and things commute with scalars. So
Yeah.
what do you mean? Whether you put it on the right? Do you mean the right or left of the equal sign?
Yeah. Okay. Yeah. I take that.
Okay,
If I take that term, I
I'm
can put
very
it,
sorry.
absorb it into 2 mu nu.
Uh-huh.
What it is really, if you like, you probably know the John Wheeler's summary of general relativity, that matter energy tells space how to curve, space-time tells matter how to move. So if you put it in a 2 mu nu, it's a source. It's what will generate the curvature. Okay. So I think that's quite interesting. Now you can take the weak field limit and you get, minus g over r squared, right? That's one thing. But there is another residual, which is lambda over 3r. So it's a repulsive force if lambda is positive. Okay. It should maybe remind you Hooke's law as well. It's a similar thing. Now, what is very interesting is that actually, little known to cosmologists, Newton already talked about a term like this. Okay, I'm not making a mistake here, it's Newton. Okay, 1687, right? And why, I don't have time to explain it. On my website, I have a semi-popular article where we actually showed why he said it and so on. You're welcome to look at that, or I can talk to you about it, coffee or dinner. But he was very, this was quite interesting that he saw both. It had to do with this shape of the planets. And apparently, according to Chandrasekhar, it's the only place in the whole of Principium where he expressed emotions, when he talked about two forces rather than one. So that tells you something. However, Einstein, as you know, put it there to achieve a static universe. It's not a static universe, so he further blind of his life, but it's good for an Eddington. Picture there. I'm a detective in a search for lambda. He actually liked lambda. And that's why the picture in Cambridge, she worked in that building for many years, well after. But and you know that joke that Eddington was asked, Professor Eddington, we have only 3 people who understand relativity, and he asked, who is the third? So that's why there are only 2 people in the picture. Now, this is again with the lambda. This is actually an extract. So the paper is in German, but there's translation in Princeton Archive. And this is actually, from the manuscript. This is the real manuscript, which is, by the way, is housed in Jerusalem. But this, you can see lambda is 11 little lambda. And then he achieved the static universe just by requesting that condition, that lambda is 1 over the radius of the universe squared. Of course, this is not a real universe, but it's still very useful as an exam problem to do that. Okay. This time is a bit limited. I won't show the latest results, but it's kind of a summary that, it's quite amazing. One paper by just one author, is leading now to all these big projects of billions of dollars, thousands of people. He kind of failed. It's funny to talk about Einstein's failing, but I don't know why he thought we just has supposed to have one value. When he talked about it as a continuous variable, he could have predicted an expanding universe and even an accelerating universe. Okay, so just that what we measure now is not the value that is a static; it's a different value. So it's kind of interesting to think why he was so keen just on a particular value. Now, putting it in slightly modern context, this leads us to this discussion now of what's going on with these new surveys over the past year or so. So for any substance, we can define an equation of state, which is pressure divided by density c squared, right? Here in this talk, C is a constant. and the scale factor is 1/1 plus the redshift. Now, if you do for that substance, if you do the kind of textbook type of exercise, you find that the density goes like a to the minus 3, 1 plus W. When W is 0, just ordinary matter, it's kind of intuitive that there's dilution with time. So this is the redshift. These are early times, this is the present. So here's the matter, dark plus baryonic gets diluted, and it comes to about this 30% or so. That's the point there. You can ask the question for what W you get a constant in density, and it has this strange value -1, not the minus. It's a kind of, because you're expanding and still you have to keep it constant. So you need this. So that's what the cosmological constant does for you. Okay. And then you can ask the question, okay, at what stage did the acceleration start? So it's about 6 gigayears ago. You can ask at what redshift, at what time or redshift matter and dark energy were equal. It's about 3.5 gigayears ago. Solar system was formed of 4.5 gigayears ago. So we live in an accelerating universe now. It was not always accelerating, okay? Now, you look at the data, and I'm really kind of focusing it until about a year ago, from different sources, which I'll explain in a moment. You read in the abstract, okay? If you just, ask ChatGPT to read all the abstracts and tell you what it finds, you'll find it's about -1, plus minus 3%. And at this stage, you decide maybe it's time to move to a different field. We know the answer, okay? However, nothing is perfect, and there's some changes. It's not exactly -1. If you read not just the abstract, but you ask ChatGPT to look at data tables, and you talk to colleagues who like to discover new things, you'll find that there might be variation with time, and this is a very popular now form to describe it. Okay, so it's a kind of Taylor expansion. There's no physics in it, but it's W0 plus WA 1 minus A, right? Obviously, if WA is 0, that's no change with time. So what happened is after supernovae results indicated lambda, there's lots of activity to start new projects. And about 20 years ago, there was a committee of clever people called the Dark Energy Task Force, and they came up with this parameterization and said, we'd like all these projects to measure these things, and those two parameters. Okay, it was a kind of condition if you wanted funding to measure W0, WA. And now we're finally at the point that we measure it. I don't know if our measurements are correct, but we got to that point, okay? So it's a story of the past 20 years, which kind of coincides with my time. I was previously in Cambridge for 20 years, worked on another survey, and moved here to do this adventure. All right.
Sorry, W0 and WA are constants.
Correct.
And A is...
It's a scale factor. It's the factor by which the universe expands.
Thank you.
And formally, we take A to be 1 at present. Okay, it's just the definition. So A is 1 at present, you just say constant. Okay, I hope you're with me. I hope there are not too many equations here. So this has led, that's what they said, this has led to many, many projects. This is only a subset. And, before there were other projects. So I was involved in 2DF, and then I moved here. And luckily, we got involved very quickly in the Dark Energy Survey, and later in DESI, and there are also people in our group working on Euclid space mission, which is out there operating. 34 papers came out in March, and LSST ground-based on a hill next to the DES telescope. Just to say that we're very fortunate, some of the work was actually done here in the physics basement of the physics building of producing what's called the optical corrector. 5 lenses for DES, 6 for DESI. Each lens is about 1 meter across, okay? And it has to be polished to the width of human hair. and be aligned this way. So just appreciate that, before we talk about philosophy, appreciate that people actually have to build these things. And also it costs a lot of money. These two, each of them is about $100 million. This other is about $1 billion each, okay? Not sure how many philosophers you can employ with that amount, with that sum, and how many problems they can solve.
Near infinite amount. You see,
Right.
We don't need the waste bin proposal.
Anyway, it's all an exciting time. All these are actually happening. Okay, well, these already produce data. Those three produce data, and this is about to operate. So it's reality, okay? And this is only a subset. This is when you translate into data, and that's why we need big data and AI and so on and so forth, is that, we got this huge number of terabytes of data and so on per night, even gigabytes, even petabytes. This is the radio facility in Australia and South Africa called SKA. We're talking about, when I was a student, I worked on a sample of a few thousand galaxies. And now, my students work on kind of 300 million or so, and soon we will have billions. And so is the price. Still only $1 per galaxy, not bad. Okay. But also look, there's also the human aspect. There's some comments in the introduction about the societal element of this. Is this, and we're going to thousands, and this is all interesting anthropology and how works group and the interaction among people. And of course, it's a question: why does the expert prepare to give all this amount of money and collaborate with the historian from Oxford? This question of the social value of doing cosmology, right? And could it be measured by cost-benefit analysis? Probably the answer is no. It's part of human curiosity, and you just do it. But are you prepared to put $10 billion? But okay, we'll leave that to another discussion. Lots is happening, in my own. Each of us can draw a trajectory. So I worked on this 2DF, and I worked on DESI and DES. It's not here because it's not spectroscopic, and a bit about Euclid. So you can see how these things work, and different individuals have chosen different. This is the number of redshifts against co-moving volume. Right? So you can just see the growth of that, and then in terms of how do you actually measure dark energy? Okay, so how do you do it? It doesn't say on the sky W equals -1. So we're lucky that there are objects like supernovae, which we can treat as standard candles. So we assume they're all the same, and if they're not the same, we standardize them. These are technicalities. There's a light curve, supernova goes up and down, we standardize them. Luckily, nature's been kind enough to create standard rulers. These are what's called baryonic acoustic oscillations, the physical features which you understand where they come from. You can predict them. And then you can use them as distances. Why is it important? Because if you have these at different distances, you can work out the geometry of space-time, okay? That's the idea. There are some other methods counting clusters. This is a nice one from the James Webb Space Telescope. How many clusters are per volume? And this is a very interesting technique, which goes back to Einstein, with lensing that distant galaxies get distorted due to intervening matter, so you can learn about the geometry as well as growth of structure. So these are the main four methods, for example, in the dark energy survey or in Euclid. Okay, we use different techniques and we try to see if they are consistent. Okay, these two surveys already talked about, where luckily, one is, I should say, these are all international projects using old telescopes from the 1970s, and they're all but very good. I experienced an earthquake, 8.3, when I was there in Chile, and the telescope survived, right? And the instrumentation survived. But these are really quite remarkable telescopes, but with new instrumentation. DES is led by Fermilab, US National Laboratory, DESI by Lawrence Berkeley Lab. And DES started, the whole thing started about 20 years ago. it coincided with my move to UCL. And next week is actually the collaboration meeting, which is the last one after 20 years. The end, it's coming to an end almost. And DESI is now at the peak activity. There will be another collaboration meeting in July. So there's already this 12 million galaxies in the bag. DESI is about halfway through. Again, this is photometric, this is spectroscopic. And this is, I already described these different techniques, a number of objects and number of people. And, that's the optical corrector, which partially was actually, I remember the date was delivered from UCL to the mountain. And we put the whole story in a book that said, why did it start? How did we get the money? How did we build the thing? And it all ends up with also sections by an anthropologist, a poet, an artist, and a philosopher. Okay, so you're welcome to look at that. You can use this weak lensing to create maps of dark matter, because this object gets distorted, and so you can do the inverse problem and figure out what's in between us and the distant objects. And you get that map created by a former student, who is still a postdoc here, Niall Jeffrey. The BBC liked it, and then more importantly, Private Eye. It's our most comprehensive dark matter map yet. So that's what you get after 20 years of work. And publicity is good publicity, right? Especially in Private Eye. Now, supernovae is also part of dark energy survey. If you like, it's a pathfinder towards LSST, which would do a much better job. But nevertheless, this supernova, there are different types of supernovae. It's called 1A. It has to do actually with the binary system of one star accreting mass from the other one, and then exploding. And we think that the mechanism is common or similar in each object because it has to do with the so-called Chandrasekhar's mass. So there's something in the physics which makes it hopefully, a standard. And when a supernova explodes, it overshines the galaxy. Okay, and in fact, we have a teaching observatory in North London, in the worst possible place on the planet. Lots of clouds and air pollution, but students discovered a supernova from there. Yeah? So, that shows you how dramatic this event is and how good the students are. And their mentor, say, Steve Fossey. So the latest is about January, I think, January 2024. The DES collaboration finally released a sample of about 1,500 objects. This is this cage you saw, which at some point was in our basement, now in the mountain, and you observed objects through 4 different filters, and this is superposition always 1,500. Okay, so you see the light goes up and then down, and it's the peak luminosity with some corrections that tells you the distance. So that's what you get. You can do all sorts of things with it. That's a very famous so-called Hubble diagram. And you look at the distance based on that luminosity against redshift, okay? And you can see it's kind of on a straight line. These data are from the low redshift is from other data set, blue is DES. Now you can do it because the people here in relativity, you can do this test of the 1% time dilation. And it seems to work. You can check, you may ask yourself, I told you that galaxies their light get distorted. What with supernovae? So luckily Paul Schau is here. My colleague has done that work, and you can talk to him what is the effect of this. But in any case, you can use them to do the cosmology. And when you force, I emphasize, if you force the W to be a constant, you get something very close to -1 to 3%, okay? So although when you look closely, you see this green line going, you would have liked it to be just a straight line. Okay, and agree with so-called Planck cosmic macro background. So it's these deviations that where all the fuss is about, okay? I want you to get the impression, if you just look at it in a very kind of broad way, you'll say, look, it's about -1. Let's sell our shares. That's it, done. But if you start looking at details, and then the question is this wiggly green line, is this because the physics is different? Or is it just because of some systematics, observation systematics? That's where we are, okay? All right, let's speed up a bit. I'm conscious of the time. It's okay? Yeah. So DESI in April 2024, just over a year ago, finally, so this is the other collaboration we're involved in, and again, the helpful corrector will be there. So I know it's a bit confusing, DES and DESI. Okay, and our data center is called DESI. So I think we need new names. But in any case, you take this map, okay, this is just a map, which of course journalists like, and it's nice to show to undergraduates. But you can do Fourier transform of that, or correlation function, and you see actually features. It's this feature called baryonic acoustic oscillation. And you can do it in 7 different places using different tracers. And you can use that feature, the size of it, which is not as small as this pointer, it's 150 megaparsecs, okay? 150 megaparsecs. If you use 2 light years multiplied by 3.26, you get in light years, millions of light years. And the amazing thing, when you actually force this equation of set to be a constant, you get again something very close to -1, ±3% if you add some other data sets. So when you read only that, you say that's it. But there are some other hints that if you allow this equation I showed you, W0, WA, it does a better fit to the data. And the situation is, this is a cartoon by one of the collaborators. And I think she's kind of captured the spirit of what's going on. So here is our dear lambda, which when I was a student was believed to be 0. Now, past 25 years was established to be, indeed there at the level of 0.7% of the budget, universal budget. But now when we have three probes, so I told you about supernovae, for example, from dark energy survey, but there are 2 other samples, and there will be more and more and more from LSST. I told you about baryonic acoustic oscillations that come from DESI, and this is the cosmic macro background from Planck, and more recently from another survey called ACT. Don't worry if you don't remember all these acronyms, but the point is we don't just look at one probe. So you can each time put a different, you can feed in a different probe, a different project, and see what it does. So the problem is with lambda, it's okay-ish, but if you allow this freedom of trajectory time, you get a much better fit. If you do chi-squared, it's a much better fit, okay, and all the numbers are in the paper. So I hope you can get that picture, that it's not that just constant lambda is completely ruined, but something which does trajectory time does a better job. Okay, so I just plotted it here in a very simple minded way. The quantity I can think of more physically is the actual density, how it changes with time. So high redshift is early time, we're at the present here. The red line is the cosmological constant, okay, normalized to be 1. So if we're all happy with lambda, it's just a constant. It's so same thing. The new results, and I have 2 versions here. One is DESI with the cosmic macro background here, which is the blue, and the other one is adding to it the supernova from dark energy survey. And these W0, WA, which are constants, the actual numbers are there. I'll show later a plot with arrow bars. But this is really, really weird, right? So I gave you this talk a year and a half ago, I would say just a constant. I'm giving it now. And look what it does. The density starts low. It's increasing as the universe expands. It's counterintuitive, right? If the density gets diluted. So this came up with the name the phantom universe.
When you say the density, Ofer, do you mean the density of the amount of matter within the space available? Is that what you're
It's the density of dark energy.
Oh, okay.
Sorry, this is dark energy, okay? This is rho dE. Sorry, it's difficult to see from there. It's just that the matter itself I showed earlier gets diluted. But the dark energy, counterintuitive, is actually getting increasing, there are actually theorems that say it cannot happen. But there are also, of course, clever theoreticians say they can fix it by putting multiscalar fields and so on. So then it goes up, and it seems to reach a peak, and then to decline. In both cases, whether or not you add supernova, the feature is the same. So, and not only that, it has to be emphasized that this W, it's actually not far away from -1 at redshift of about 0.5. That's, I think, why you get this. When you're forced to be constant, you get that because most of the data are there. But, we're still discussing it a lot. Paul and I and many others, very busy Slack channels within DESI discussing that. Okay. So, how significant is the deviation from this constant lambda? Is a phantom universe physical? This thing that is going up, and why is it about -1 at when you have most of the data? Okay, this is some information just with in physics seminar. Someone always asks, what about the error bars? So I have to show that otherwise, but maybe philosophers can take a higher view. So this is with the error bars. This is actually from a paper, one of the papers that appeared in March 19th. There was also press coverage and so on. So again, you can see the W is a crossing at about of -1 towards the phantom. You can see that thing in terms of density of the dark energy going up and then down. And this is the acceleration, okay? And this is another more parametric version of this W0, WA, that this is the model we've kind of learned to live with for 25 years. And now the data, different combinations tell us it's far away from it. It points at it, but it's far away. And then, I know there's some particle physicists here, 4.2 sigma, do you lose sleep over 4 sigma? Particle physics tell me they take something seriously on about 5 sigma. But astronomers, is this true?
Never trust a particle physicist.
Okay. Well, astronomers are more adventurous. Already with 3 sigma, they contact journalists, So that's what's happening now, That's what's happening. You have to appreciate that. So, indeed, here's the media. This is March 19th. Lots of coverage, Guardian, respectable outlets, Guardian, BBC, and you can see what angle how journalists play with it. Is dark energy experiment challenges Einstein theory of universe. Okay, so it's very careful, maybe. And personally, I don't think this shows Einstein is wrong. Just maybe something to understand. And Guardian seemed to be even more poetic here. Mysterious cosmic force appears to be weakening. Okay, so what they mean is this. Maybe it's easier here. They mean this decline. Okay, here it's actually going up. It's this decline that they're referring to. Okay.
What axis there, Arthur? So I can't see it from.
Sorry?
Where's the x-axis?
That is the redshift.
Okay.
So this is early time, current time, and since redshift by 0.5, it seems to decline. Okay, so that's a story. So there are many questions. Should lambda be just -1? Maybe some deep connection to quantum fluctuations and so on. Is it left-hand side or right-hand side? Is it physical for it to be less than -1? What's the case for time dependent? When should we stop with this game? Are you happy to put $10 billion for another operation? They tend to the unpending discrepancy. Now, this anthropic principle, I don't know if this conference will go that way, but we can talk about that. We won't live in the universe. We won't be the way we are unless the universe had those parameters. And maybe there's a room for a higher level theory. And I don't know, I'm speaking here, there's lots of hand waving, but I think this lambda is some connection between gravity and quantum mechanics. It's ought to be, if the lambda comes from quantum fluctuations and it's part of mu, this is the connection. But so then in the last 2 minutes, it's okay, just to say, of course, we're in a new era, and one can just think this is just a hand wavy thing. to say, but AI, which some I like to say augmented intelligence, but sort of taste. But there's been laws of physics which we believe are there regardless of us, unless you believe in tropic principle. And there's all this human knowledge and how to combine them. I think it's very interesting now. So you hear people say, "Oh, it's all going to be robotic. We don't need any more anything. We don't need humans. So everything will be, operations in hospital and referring of papers and everything will just be done." Or you can say, let's incorporate that. So it's kind of what's called physics inspired. Yeah. So a lot is going on here, just advertising it to our friends from Helsinki. A lot is going on here. Many staff and students, postdocs, are using AI. And we have a center that I co-direct with particle physicists and others, where we basically train the students, about 10 per year. They get it's a dual career. They end up 4 years, they do a project in astronomy or particle physics, but also 6 months in the industry. So they will work in the Guardian newspaper or in Fusion, or one of my students now in the Treasury for 6 months. So it's bringing together all these concepts. This is just a commercial. We'll have a conference here at UCL on the 30th of June, which I believe coincides with your workshop in memory of Basil. So sorry about that, Crash, but that's a lot is going on, but it's 3 days. So those are interested, welcome. I think it's still a question. AI, I think of it as a set of hammers and the nails. I mean, it's in other fields like porting, folding, and materials, it's really made a revolution. Without offending my colleagues, I think we've not seen the revolution yet. We can no longer do astronomy without machine learning, without these billions of galaxies, we cannot do. But have we seen something that, wow, it's a new theory came out of it? I don't know. Could AI reproduce GR without us knowing about GR? Questions like that. So I think it's an interesting time. So I think this is my summary slide. I think based on observations, Einstein was right that lambda of some sort exists. He was wrong about its value, okay? Because people ask that question all the time. Now we don't quite know if it's exactly lambda, okay? So I took a rather conservative view here that it's supported, but we've just seen that there are also deviations from it, okay? It is at most at the moment 4.2 sigma. So it's important to continue more, and I think we are in some golden age for cosmology because there are all these projects. So for young people, it's an amazing playground. Maybe with these new results, we see a new paradigm shift. Our poor students, they've never seen a paradigm shift. Maybe if it just grew up, I grew up with the lambda equals 0 period. They grew up with the lambda constant. Maybe the next generation will live with a new paradigm shift of a chain, lambda or something else. I haven't talked about neutrino mass. It's another thing that came out of DESI, the particle physicists might mention that. Again, there's a peculiarity there that if you allow it to be completely floating, you get a negative neutrino mass. Let's talk about coffee. Interesting enough, if you put W0WA, there's more freedom and it's less of a problem. So there's some crosstalk there. It's for another discussion, but this is a very exciting time because we have the results from neutrino oscillations, and now the cosmology gives an upper bound that are very, very close together. AI for cosmology, I think we're still waiting for a killer application, if I have to be honest about it, but it's there. And this is, I allow myself the last one, our philosophers here. Maybe our brain is just limited. Our bandwidth is just limited to figure out the universe. We think we could put all these telescopes and measure, but maybe when it comes to understanding it, think about my daughter's dog. He cannot figure out quantum mechanics. We think. We think. So maybe we're also limited, and maybe AI could be the new tool to give us a kind of an extension, to give us a pair of glasses to maybe seek relationships in the data or some fundamental theories which we still haven't figured out. And I'll stop here on this optimistic note. Thank you.
Thank you very much. Yeah, there's several questions that come on. But just, given that I have the power, can I ask you one question?
Sure.
Before is sorry. Yeah. Okay. So the question I have is your WA. How are they chosen? Yeah, because you had values there at some point when in your graph, and you know. Yeah, these ones here. So that graph here. So
Yeah.
you chose these different.
Yeah.
So are they part of the fit?
Yes.
Okay.
This is the result of the fit. Okay. So essentially, it's that diagram.
Yeah. Okay.
So this is the result of a very elaborate statistical analysis, Bayesian analysis. So you put the kind of likelihood functions and priors. That's important. You put priors and the Bayes theorem using MCMC, Markov chain Markov. Then you get this type of diagrams, and you read it off. So there's a big long table.
Yeah.
And then the interpretation is a bit frequentist actually, going back to p-values and how many sigmas. Happy to discuss again. Particle physicists have their own experience with that. But that's, so it comes from a fairly
But the physical meaning or the physical reality of these things, doesn't that give you certain bounds on what's allowed here? Because it's a big range of the other thing. You're talking about this and that as the range. So does that
So people use in the papers as kind of priors, because they cannot be less than something, cannot be more than something.
Okay.
So that's that point. There are also, by the way, other parameterizations. So these are of the 8 papers that appeared in March. One of them looks at 5 or 6 different parameterizations, including the speeds, without any non-parametric and molecular elements.
But they don't give you any physical information.
For the physics, you can then do the game of taking a physics model and say, in that physics model, what would W0 be?
Okay, but
For example, scalar fields, you can translate. Okay? And in some models, W less than -1 is not allowed, for example. Okay, so it's a whole industry of connecting. Okay, thank you.
Can I just make one comment about neutrinos? I can't give you a reference on that. There is actually, they've actually been set a lower bound as well as an upper bound.
Correct.
So therefore, going below the lower bound would appear to be off the table. I'm saying appears, but
Right,
I'm not making definitive statements.
No, you're
There is a
absolutely right.
lower
So,
bound as well as an upper. It's somewhere in between, and where it is in between, that's the bit we don't know. And the other thing you need to be careful of with neutrino mass, of course, we have 2, in the sense of we have the flavor, which is the way we observe neutrinos, but the whole neutrino oscillation theory is based on 3 mass states.
correct.
Which, as far as I'm aware, we don't really have much information on, because you only get information from when they're mixed together. So one has to be a little bit careful.
Well, so there's a whole other paper in that series, which I'll send you a link to,
Yeah, sure.
which goes exactly through what you just said. In short, if you take oscillations and normal hierarchy, oscillations as in neutrino oscillations, you get the lower limit, as you said, it's 0.06 EV.
Yeah, I can't remember.
And the cosmology gives you something like 0.07 now. Okay. But if you're just an open-minded cosmologist, say, I don't want to think about the oscillations, you allow it to float, you get a negative value. Okay? Which might be systematics, okay? So that's why it's all,
I'm just saying, it's a
believe me, we're all puzzled.
statement to make.
Well, I'm not trying to sell you, to tell you neutrino mass is negative. I'm just saying that it shows some sensitivity to the
Well, it's
data.
so close to zero, that's the
Yeah.
trouble.
Yeah.
And that's the reason
That's
why
it.
we went from frequentist to Bayesian statistics in, well, I say the reason.
Yeah,
not
yeah,
the-
yeah.
One of the reasons is because with frequentists,
Yeah.
once you put an error on, it takes you into the negative mass region.
Right, right.
And we felt, I say we, this is
Yeah,
the
yeah,
world,
community,
we did,
yeah.
you know, that's not
Right.
that's not physical.
Okay.
We think that all masses are positive. And so that's why there was priors put in
Yeah.
to say you can't go below that.
Can't go
That's
below.
where the Bayesian methodology
Yeah. Yeah.
started to really come in. But
Yeah.
it was really to do with neutrino masses.
It's all very much the focus of the discussions, and I'll send you the relevant link.
Good. You wanted to ask a question, and afterwards, I think Tuomo. So there'll be a few questions directly. No. Then we'll
I'm
have a
still-
kind of. Yeah, you stay there.
You're still here, all right, fine, okay.
This is a two-parter and more of a comment. So Rob is actually more of the particle physicist. I would say I'm a high-energy physicist who does more in cancer than he does anything to do with particle physics these days, which means I can maintain a healthy skepticism. So the thing about that 3 sigma, or if you require a 5 sigma in particle physics, as a skeptical outsider to particle physics, if you believe that all of the experiments that you do in particle physics are because underlying that is a quantum mechanical theory that is fundamentally statistical, all you have is statistics. So if you don't have any knowledge of any underlying dynamics below the statistical distributions, then all you can do is rely on experiments that throw more and more statistics in, and then you have to rely on a statistical distribution that gives you something above a certain level. If you search for something with a bit more intelligence of the underlying dynamics, then I think that limit comes down somewhat. So I think both approaches are valid, although I trust more having some understanding of the underlying dynamics.
Right. But the narrative here is that lambda CDN is it's been around for 25 years. Lambda goes back to Einstein. So this bit is like the null hypothesis. Okay, that's the way you say it. That's null hypothesis. And you check how far away you are from null hypothesis. But we still don't have a good theory for lambda, you can argue, right? So,
In many ways, Simon, what you've just exposed is this fundamental difference between classical and quantum. And this, I'm not saying anything's right or wrong here. I'm just saying this is exposing where you get the two coming together.
Yeah.
And as Simon says, quantum mechanics is fundamentally a statistical theory,
right.
whereas we know GR and so on is we call it a classical theory. And so therefore, when you start to get this situation, there's no great surprise there is the tension. Because the two theories are, this fundamental difference comes out. And so therefore I'm not surprised there was a tension. And as you quite rightly say, you go, well, these are the results. You decide what you feel and you believe.
Yeah.
And that's it.
Well, and the third ingredient are of course systematics, right? The data
Well, yeah.
errors.
Sorry, that was, yeah.
That's also
How
important,
good your
right?
instruments are.
We had another type of tension in the field, something like the fluctuation of the fluctuations of the mass, right? There's a parameter called sigma 8. For 2-3 years, people talked about tension. It just got resolved.
Oh, really?
Yeah, they just fixed something in the analysis. They're done blinding all that. We heard the seminar yesterday. Gone. So things also go away. Okay, 3 sigma also go away. But I think let's summarize it. It's an interesting interplay with the data, quantum mechanics, relativity. I think it's a good way to think about it.
So the second part of my question, and I'll be brief with this, is talking about AI. I dine out on this quote that I came up with. There's no I in AI. So intelligence is the input data. So because we have exactly the same discussions in cancer biology, in gene markers, in radiotherapy treatment planning, is how much you rely on the computers to do the predictive work. In other words, interpolation, great. So the augmentation, I think augmentation is a good word, with the pattern matching of what you already know and what you can see and bringing out patterns, excellent. Extrapolation to new theories, let's say I'm doubtful. So there is still space for you and the dog to solve the theories, because it requires that creativity. So the one thing that then I'm interested in from your perspective is the theories that you are applying to very distant measurements rely on, at some level, a local experience. And how much you can extrapolate from very precise measurements that you can make in the local physical reality to something at great distance that then has the implication for your local physical reality.
So this is usually, they're all very good points. It is a huge area of simulations. Okay, the fake universe, but people put a lot of effort in groups. We don't do it ourselves, but well, some there's actually a group doing that. They're even called the Gower simulation, Gower simulations. But it's a whole area of simulations, and then it's comparing the two and see do they make sense, and that's the AI could help with that comparison.
Thank you.
Okay, thank you, Ofer. So the idea now is that Tuomo and we're going to have a kind of general question and answers kind of dialogue on what you've sort of been presenting lately. Yeah, thank you. Yeah. Thanks.
Okay, thank you very much. So I'm in a certain sense in a happy position because I'm trying to understand Tuomo's theories and ideas, and then just communicating them. I might evaluate something, but I can communicate, and then we can discuss about these ideas. So in science, we are in good position in a sense that we have common empirical data, but we might have different interpretations of that data and different institutions analyzing that data. But here's the Pantheon Plus data set that also you showed. So the black dots are the Pantheon dataset for supernova type 1A brightness observations. And this is called distance modulus, so it normalizes the absolute magnitude of the supernova. So for astronomists, this higher magnitude is dimmer. And then the vertical axis is or the horizontal axis is the redshift. And it just tries to measure the wavelength expansion, how it's observed, some standard like hydrogen spectrum or some other aspects. And further you go to the right, this more distant is. So in this picture, I plotted from that Pantheon paper those lines, and they are really close to each other. There's some scatter. I didn't plot any error bars there because there's already some scatter in that dark black dots. But it's very difficult to fit these models so accurately in that data. So they used like covariance matrix, really like accurate predictions. And now the thing is with Tuomo's model, that there is this, Tuomo has derived from purely like geometrical principles from that we can go through this kind of a model. And one can perhaps think it as like a phenomenological model. One doesn't need to take into like ask about the actual physics, but it might imply some physics. And the thing about this model is that there's only a single parameter. So there's only the Hubble distance, RH, which is currently, I haven't even made any fit here. I just put the 13.8 billion light years. And then to make this work, you have to, this 10 parsecs, you have then also this Hubble distance, you have to express it in parsecs. Another problem here is, because it's so difficult to search literature for formulas. It's difficult to know, is this novel, is this known, is this a known approximation, and also can we rule this out? Because I haven't even tried to make like a really accurate estimation of this, because those who already have those supernova analysis pipelines, they should do it. But now we can. I have tried to analyze it a little bit, in a sense that when there are different kind of cosmological models, they sort of tend to go towards this Tuomo's model, but there might be vertical bias in this, so be careful with that. And also there's this novel new supernova observation at redshift 3, and it sort of goes towards that Tuomo's model. But we can't really trust that, because there can be like vertical bias in this. But the thing is that Tuomo thinks, and we can just study it as an hypothesis, as a suggestion at this point, that you can actually you can factorize this, like this is algebraically correct. You can factorize this to these two terms. And Tuomo thinks that actually this term here is accidental dimming in the data due to the K-correction and other processing in the data. And I haven't been able to rule it out. But we can discuss it a little bit. But this has the same form as the K-correction in the really old papers. But also there's this quite weird thing that if one, for example, reads Anderson how they motivate K-correction, which is apparently used in this data, they say that the K-correction accounts for the difference between the observed apparent magnitude of a source and the apparent magnitude of the same source in its co-moving emitter inertial frame. So there's this kind of a comparison going on instead of thinking about actual luminance and then physics, how it's observed. And the difference is caused by two effects, they say in that paper. A systematic shift of the spectral energy distribution incident on the photometric filter. So bluer parts of the emitted spectral energy distribution pass through the photometric filter, of course, because it's more redshifted. But then this dimming effect due to the fixed width filter are very compressed when viewing from the source. And this is, I guess, if there's that kind of thing, it's a little bit problematic in the sense that now the data has been processed in a way that it's not theory agnostic anymore. Because there's some priors in the data. Because when you start then comparing different kind of cosmological models there's already this kind of rest frame, like this kind of like reciprocity theorem, like implicit into the data in some sense, if this is true. But it is really difficult to find, because for example, in supernova analysis package, there's 10,000 line K-correction C. And especially it's as a quadratic term, you can very easily get it from different parts of the analysis pipelines. For example, the AB magnitude, which use Jansky's, they are defined for a constant hertz, constant frequency. And then when you analyze it in terms of wavelength, you get this quadratic, to the differentials, you get the quadratic effect. So it's difficult to think what is happening there. The technicalities of various zero points and photometric systems, and also photon counts versus energies, do you use HF or the energies directly. Then there's the stretch factor, which is already 1 plus Z. So it's a difficult thing. And I analyzed this DCAM filter data that you also mentioned. And these are the actual flux counts. So these should be the observations at each redshift through 4 different filters. And I would have expected that this is the Tuomo's model. So it's like a brighter model. So I would have expected that the fluxes would have been there. But they are actually already dimmed. So there's something that I don't understand about the data. Either there is K-correction somehow already involved in this original data, or then there's something that I don't understand about this situation. Also, the Tonry table has, from 2003, has these kind of curves which express like bolometric magnitudes or like magnitudes seen through different filters, and it just seems like it has this kind of an envelope curve. And this is actually just the Tuomo's model, and then this is the Dimmed model that is actually then reported. But here also I don't know if there are like different references for different bands. So is it actually shifted up because there's different references? But Tuomo has made a simulation. How is a black body spectrum seen through those filters, like ideally, and he got these results that seem to match with Tonry's. But this is just because this is such a huge important thing, I can't claim any like that's how it is. But it's just that I can't rule it out. And now to look at it, so we can actually draw this plot this in this sort of k-corrected or this original data, and also this kind of non-k-corrected or this kind of like brighter data. And this is like a big question: is the data really like brighter than we think? And that's something of a research question that should be addressed. But now let's go this how Tuomo thinks that this actually is derived, or what is this structure of this. So he actually thinks it in terms of like classical physics. So he thinks that this here is the bolometric flux. So this is the bolometric flux, so it's watts per square meter. And then when you have the flux, the luminosity at the source, the luminosity is normalized here by subtracting this m. But then there's just like a normal inverse distance dilution. So inverse distance, because the absolute magnitude is defined at 10 parsecs, and then the inverse distance just dilutes the power. And then because of the redshift, the power is diluted, because the cycle of radiation carries the same amount of energy, but it's diluted because it's the larger wavelength. So only, for example, half of the wave comes through. It's not like that, but that is how Tuomo thinks about it. And now with this, you actually get optical distance. So this D has this kind of a really nice algebraic form where there's the Hubble distance and there's Z1 plus Z. And this saturates at Hubble distance, and this is sort of like the light travel distance in standard cosmology. And also then the redshift relation is satisfied because the observed lambda divided by emitted lambda is by definition 1 plus Z. And then this is quite nice that it's the current Hubble radius divided by the sort of like a Hubble radius at the emitter, or when it was emitted. So this is like that kind of a sort of almost Minkowskian like a relation. And now here, if you here solve for D, you get this, and if you put this here, you get this, and if you add this dimming, you get this. And now this is quite interesting because this is like completely like geometrical like derivation. And if this for some reason happens to be true, then there's new kind of a phenomenological model is available where there is no extra parameters. And that is something that really and yes, and I can also show what kind of geometry this would then perhaps imply, this Tuomo's geometry. So in a certain sense, these light cones. So in a certain sense, the light travels the Hubble distance during that Hubble time, but also the space expands that time. So that's why they are they are like linked. And one way of conceptualizing it is that currently we think that the cosmic microwave background radiation and everything, we receive it at the center, or everything is due to cosmological principle at the center. And there's a small problem of this cosmological horizon and why inflation is there. And it's a metric expansion, so you don't actually feel the expansion. And during the expansion, there has been like a really big like a timeline. What has happened? We have to always think about that. I'll keep it there as a reference. And now in Tuomo's model, we actually think that we are at the edge of the universe. So we are always like traveling with this expanding space, and then because the light travels at the same speed as in tangentially and radially, then this tangent of this curve is 1, so it's 45 degrees, like a space diagram. But because it's always that same, then it curves this kind of, it starts here, and then light curves in these kind of logarithmic spirals. And this is quite interesting because this is like a scale-free model, and it's then a finite universe. This like space-time is foliated into this kind of space like 3 spheres. So it has an explicit formula, and there's a lot of questions. Then what is the CMB? Because you are seeing something there, and actually light can travel like multiple times in the early universe. So it's like I don't know about the acoustic oscillations or either that kind of scale-free behavior there. So this is like really like a open question. And the thing is that the 3 sphere is such a fundamental that you can either model it as in this kind of 4-dimensional background space, or 2 complex numbers or quaternions, and then there are exactly 3 linearly independent vector fields which are non-vanishing and nowhere zero and non-linear. So it's a really regular structure. The U1 and SU2 symmetries, and then these idempotents are also related. And then you get these formulas where the angle and the radius emitted and radius observed, because this is you can at any point the relation is the same. You get this relation here, so you have a really like it sort of has this kind of a quantum mechanical feel to it in a sense, because it's scale free. So then it actually might even appear here in some sense. And Tuomo just Tuomo does a thing where even though the speed of light is constant, he defines a separate time scale where speed of light is variable, and he thinks that this is actually the proper like true time in a sense. And then you get, sorry that it doesn't show, then you get the dynamic equation for the radius, dynamic equation for its derivative, which is here this speed of light. You can get the angular frequencies, and you can even take the time. Actually, you can infer the time from here, and all this is come just from analyzing this formula as a differential equation. Yes.
Okay, I think this covered very well, so that I make a short comment.
Okay.
Yeah, otherwise we are running out of time.
We are now, but don't worry. So, yeah, so thank you very much. I don't know if Ofer, do you want to say anything, or did you have any comments? Yeah, please. Yeah.
Sorry.
Do you have the mic?
Well,
Well, thank you very much. It was very stimulating and interesting. So I'm involved in supernova studies, I would say, and more on the data analysis side, the data reduction side. But I can offer a couple of comments on the data reduction. we observe supernova in two ways. We observe broadband fluxes, green, red, I, Z, and we also observe the spectra. So we have the redshift of a supernova from observing the spectral features. Now, a model is constructed using observations of nearby supernova, which we think we observe reasonably well. So what you describe as K corrections in the pipeline process is the fitting of our observations to templates which are derived from nearby observations and the knowledge of what our filter characteristics are. So that's the basics of the data reduction. At that point, more or less the physics leaves the process. The rest is more or less empirical. We observe that bluer supernovae are brighter than redder supernovae at the same redshift on average, and that explosions that last longer are brighter than ones that are shorter, again at the same redshift. But this is all empirical, and the understanding of what physical processes may generate this is very imperfect. The last stage of a process is the production of distances. And again, this is largely empirical. Yes, you're quite correct that a theoretical prior has to come in at some point. We have to have some place to start the analysis process, but a considerable amount of effort is put into ensuring that that starting point does not contaminate the end data. Of course, one can quibble with aspects of this and say, well, some contamination may be inevitable, but a considerable amount of effort is put in by the people who make the data reductions. Now, the good news is that therefore, and you are quite correct to say that there are many different forms of models and expansion histories that can fit supernova data. We produced a supplementary paper to the main analysis paper that explored some of these different models. Some of them have nothing to do with dark energy. Some of them are vaguely motivated by string theory. Some of them are vaguely motivated by interactions. So whether you might have dark matter decaying into dark energy or that kind of flavour of stuff. To be honest, again, a lot of this stuff is empirical. This model could be straightforwardly tested. There are principle Bayesian ways to do this. The advantage of a model is that there seems to be few free parameters in it, and it can be straightforwardly tested, and one can obtain a confidence in this model versus any of the other models. And again, I personally view W0 WA as not a physical model. That there are in fact a lot of problems in viewing it as a physical model, and Ofer touched on some of those. It has been pointed out, for example, that the DESI solution violates the null energy condition in general relativity, which of course is problematic. I would say there is a lot of space to test alternative models, a lot of interesting proposals that are already around the community. This can be tested.
I agree, yes. Science.
Yeah.
Thank you, Petri, for the very careful analysis. May I shortly comment how I came to the prediction? So that going back to 1930, when Tolman presented the luminosity distance and luminosity to be observed, he was a real scientist, and he was careful in interpreting all new ideas in physics, such as special relativity, general relativity, Planck's equation, and Doppler effect. And the choice was, in his paper he stated that evidently we should take this like this way and the other way. And his final choice was that he uses the co-moving distance as the aerial dilution. And in my perspective, we should use the light travel distance, which I call the optical distance, which is a very, very simple form in the dynamic universe. There are no extra parameters at all. It simply comes from the geometry. And the other is the interpretation of Planck's equation, because if we write Planck equation in form h is equal to h divided by t, it tells that the energy carried by one cycle is constant. So the only dilution we have is once the effect of redshift, not twice as Tolman. So that when I differ when I compare the DU prediction and standard prediction, there comes that in my case I use optical distance and only single dark energy dilution. And in standard model, they have longer distance and twice the redshift dilution. And that's in fact compensated with a co-correction. And I made some simulation and analyzed the effect, and I came that they balance each other indeed. And so my conclusion was that in the DU perspective, when we have a very simple geometry and easy interpretation of the dilution factors, we get the correct result. And then we don't need any dark energy or other parameters at all, or any. There's also assumption of the flat space condition, which in fact is exactly the same as zero energy condition. So that we can say that the flat space is a kind of geometrical interpretation or critical mass condition, and the zero energy interpretation is like a dynamic one. Okay.
Something else?
To relate it, to just understand the procedure. I mean, obviously, let's remind ourselves, supernovae are still, we use them in an empirical way. It's not like baryonic oscillation in this physics. There's lots of unknown astrophysics, but in the supernova itself and between us and the supernova. But I'm trying to understand, after all, when it comes to all these corrections, they have to be the same in what you do and what, for example, Pantheon or DES do. So, Paul mentioned some of the corrections and so on. I'm trying to understand, if you use the same correction, you don't need to put any cosmology anymore except for your model, right? You say you don't need lambda, you don't need dark matter. You just put your model and the systematics. But are you using the same correction for systematics as in the supernova papers?
No, actually, because we are.
You do it differently. Obviously.
Yes.
So what I'm advocating is that let's do the systematics the same way. Because that's not about cosmology. You know, if it's dust or K correction, so do it the same and look what the difference is then. Otherwise, it's not like with like.
Good. We're going to move on because we're only 10 minutes late, I think.